Why does anything exist at all? No, really, think about it. You, me, this screen, the chair you're sitting on, the air around you. Why is any of it here? Why is there matter? Why are there atoms? Why doesn't everything just collapse into nothing? Most people never ask this. They just accept it. Things exist. That's obvious. Look around. There's stuff everywhere. But that's not an answer. That's just pointing at things. When you actually dig into why matter is stable, why atoms don't collapse, why the electrons don't just fall into the nucleus, you discover something so strange, so completely alien to everyday experience, that it changes everything you think you know about what existing even means. Matter exists because of a rule, a quantum rule, a rule that says two electrons cannot be in the same state. That's it. That's why you're here. The Pauli exclusion principle. When you understand what this really means, when you see how bizarre it actually is, you realize the universe is nothing like what you thought. Let me show you what I mean. Let's start simple. An atom. Take hydrogen. One proton in the nucleus, one electron around it. Where is that electron? You probably picture it orbiting, like a planet around the sun. That's what they show you in school. Nice diagram. Electron going in a circle. Simple. Wrong. The electron isn't orbiting. It's not at any particular location. It's not moving in a circle. It exists as a cloud, a probability cloud. It's everywhere in that cloud at the same time. All of it. Simultaneously. Wait, you say. That's just because we don't know where it is, right? It's really in one place. We just can't measure it precisely enough. No. This is what everyone thinks at first, and it's completely wrong. The electron is not in one place that we simply don't know. It is actually, truly, physically, in many places at once. This isn't ignorance. This is reality. How do we know? Because we can test it. And the test is beautiful and simple and utterly devastating to common sense. Take a beam of electrons. Send them toward a barrier with two slits in it. The electrons go through. They hit a screen on the other side. You see where they land. Now, if electrons are particles, little balls, they should go through one slit or the other. You'd see two blobs on the screen. One blob behind each slit. That's what particles do. But that's not what happens. You get an interference pattern, bright and dark bands, stripes. This is what waves do. When waves go through two slits, they spread out, they overlap, they interfere with each other. Where the waves add up, you get a bright band. Where they cancel out, you get a dark band. Water waves do this, sound waves do this, and apparently electrons do this too. Electrons are waves. But wait, you say, okay, maybe it's because there are lots of electrons interfering with each other. Fine. Send them one at a time. One electron, it goes through. It hits the screen. One dot. Like a particle. Send another dot. Keep going. One electron at a time. Dot by dot. Build up the pattern slowly. Surely now you'll get two blobs, right? Each electron is alone. There's nothing to interfere with. Wrong again. The interference pattern appears. Slowly, dot by dot, the stripes emerge. Bright and dark bands. The same pattern you get with waves. But how? Each electron went through alone. There was nothing for it to interfere with. Unless each electron went through both slits at the same time. Each electron interfered with itself. It was a wave. It spread out. It went through both openings. The two parts of the wave overlapped and interfered. And then, when it hit the screen, the wave collapsed into one dot, one particle in one location, one electron, two slits, both paths, simultaneously. This should break your brain. This is not a metaphor. This is not an approximation. This is what actually happens. We've done this experiment thousands of times, with electrons, with photons, with atoms, with molecules hundreds of atoms across. Same result every time. The particle exists in multiple places at once. It takes all possible paths simultaneously. Only when you measure it, when you look, does it become definite. Now here's where it gets even weirder. You think, I'll be clever. I'll watch which slit the electron goes through. I'll put detectors there. Do it. Watch the electron as it approaches the slits. The detector clicks. You see it go through the left slit. Just the left one, not both. It's a particle after all. Look at the screen. The interference pattern is gone. Now you get two blobs. Exactly what you'd expect from particles going through one slit or the other. No interference, no stripes, no wave behavior. By watching, you destroyed the interference. The act of measurement changed what happened. When you don't watch, wave behavior, both slits, interference pattern. When you do watch, particle behavior, one slit, no interference. The electron knows whether you're watching. Measurement changes reality. This isn't some experimental error. This isn't a problem with our instruments. This is nature. This is how the universe works at its most fundamental level. Richard Feynman said this is the central mystery of quantum mechanics. Everything else, all the weirdness, it all comes from this. Particles are waves. Waves are particles. Things exist in superposition. Measurement creates reality. And here's the thing that drove Einstein crazy. It's fundamentally probabilistic. There's no hidden mechanism underneath, no clockwork, no determinism. The electron really doesn't have a definite position until you measure it. Not because we don't know, because it doesn't exist. Einstein spent decades trying to prove this was wrong. He said, God does not play dice with the universe. He thought there must be hidden variables, something we're missing, something that would restore order. He was wrong. Experiments proved it. Bell's theorem, Bell's experiments, quantum entanglement tests, all of them confirm there are no hidden variables. The universe really is probabilistic. This is bedrock. But here's what makes this more than just philosophical weirdness. Here's where it connects to why anything exists at all. Back to the atom. Hydrogen, one electron around one proton. The electron is in this probability cloud, this quantum state. Why doesn't it fall into the nucleus? Classical physics says it should. The electron is negatively charged. The proton is positively charged. Opposite charges attract. The electron should spiral inward and crash into the proton. Every atom should collapse. Matter shouldn't be stable. But it doesn't collapse, and the reason is purely quantum. The electron is a wave, and waves have wavelengths. For the electron to exist in a stable orbit around the nucleus, its wave has to fit. It has to complete a whole number of wavelengths around the circle. Otherwise, the wave interferes with itself destructively and cancels out. Poof. Gone. Only certain orbits work. Only certain wavelengths fit. Only certain energy levels are allowed. The electron can't have any arbitrary energy. It can only have specific values, quantized values. This is why it's called quantum mechanics. The electron can't gradually spiral inward because there's no gradual. There are only specific allowed states. The electron jumps between them. Quantum leaps, not smooth transitions, jumps. And the lowest energy state, the ground state, the electron can't go any lower. There's no state below it, so it stays there. Stable, forever. Atoms exist because of quantization. Matter is stable because electrons can only occupy certain states. But now add a second electron. Helium, 2 protons, 2 electrons. Both electrons want to be in the lowest energy state. That's where they'd have minimum energy. They should both go there, but they can't. This is the Pauli exclusion principle. 2 electrons cannot occupy the same quantum state. If one electron is in the ground state with a certain spin, the other electron must either have opposite spin or be in a higher energy state. Why? Why can't they be in the same state? Because they're fermions. because their wave function has to be antisymmetric, because swapping two identical fermions introduces a minus sign, because honestly the deep reason is buried in the mathematics of quantum field theory and it's not intuitive at all. But the consequence? The consequence is everything. This is why matter has structure. This is why the periodic table exists. Electrons fill up energy levels. First level, 2 electrons max. Second level, 8 electrons max. They can't all crowd into the lowest state. They're forced into higher states. Each element has a different configuration, different chemistry, different properties. Carbon has 6 electrons. They arrange in a specific way because of the exclusion principle. That specific arrangement makes it possible for carbon to form 4 bonds, chains of carbon atoms, complex molecules, organic chemistry, life. You exist because 2 electrons can't be in the same state. And here's the really crazy part. This same principle, this exclusion, is why matter is solid. When you touch a table, when you feel its resistance, you think it's because the atoms are physically bumping into each other, like billiard balls. No, atoms are mostly empty space. The nucleus is tiny. The electrons are far away. There's nothing there. When your hand gets close to the table, the atoms aren't actually touching. There's still empty space between them. What you feel is the exclusion principle. The electrons in your hand and the electrons in the table are both fermions. They cannot occupy the same states. As your hand gets closer, the electron clouds start to overlap. The exclusion principle says no. The electrons resist. They push back. Not because of a force in the classical sense, because of quantum mechanics. Because the wave functions can't overlap if it would put electrons in the same state. The solidity of matter is a quantum effect. The resistance you feel when you touch something, that's the Pauli exclusion principle. That's the universe enforcing the rule that identical fermions must be in different states. Everything solid exists because of this rule. Now, light, photons, they're bosons, not fermions. They don't obey the exclusion principle. You can put as many photons as you want in the same state. That's how lasers work. All the photons in the same quantum state, all oscillating together, coherent light. But electrons, fermions, they must be different. And this connects back to the double-slit experiment, to superposition, to the fundamental weirdness of quantum mechanics. The electron going through both slits is in a superposition. It's in 2 places at once. But when you measure it, the superposition collapses. It becomes definite, one location, one state. Why? How does measurement work? What counts as measurement? Nobody really knows. This is the measurement problem. It's been debated for a century. Copenhagen interpretation says measurement collapses the wave function. Many worlds interpretation says the universe splits. Pilot wave theory says there are hidden variables after all. We don't know which is right, maybe none of them. The mathematics works perfectly. The predictions are flawless. But the interpretation, the meaning, still uncertain. Here's what we do know. Quantum mechanics is the most successful theory in the history of science. Every prediction confirmed. Atomic spectra, perfect match. Chemical bonds, completely explained. Semiconductors, transistors, computer chips, all of it comes from quantum mechanics. The device you're reading this on exists because we can manipulate quantum states. We can engineer with wave functions and superpositions and exclusion principles. And the experiments keep confirming the weirdness. Quantum entanglement, 2 particles connected such that measuring one instantly affects the other, even across vast distances. Einstein called it spooky action at a distance. It's real. We've tested it over hundreds of kilometers. Quantum tunneling, particles passing through barriers they shouldn't be able to cross. The sun shines because of quantum tunneling. Nuclear fusion requires particles to overcome enormous electrical repulsion. They don't have enough energy. But quantum mechanics says they can tunnel through, and they do. All of this, all of it, comes from the same foundation. Particles are waves. Things exist in superposition. Measurement matters, and identical fermions cannot be in the same state. So why does anything exist? Because quantum mechanics makes matter stable. Because electrons can only occupy certain energy levels. Because the exclusion principle forces structure. Because the universe at its most fundamental level is not made of tiny billiard balls, but of probability waves that collapse when you look at them. This is the avalanche that started with Einstein and the photoelectric effect in 1905. Light is particles, then Bohr's atom, electrons in quantized orbits, then Heisenberg and Schrödinger building the mathematical framework, then Pauli discovering the exclusion principle, then Dirac unifying it all with relativity, then Feynman reformulating everything in terms of path integrals, then the experiments, thousands of them, each one confirming something that should be impossible, and we're still going. Quantum computers exploiting superposition to calculate things classical computers never could. Quantum cryptography using entanglement for unbreakable codes. Quantum sensors measuring with impossible precision. The universe is not what you thought. It's not solid, it's not deterministic. Things aren't in definite places until you look. Matter exists because of rules that make no sense in everyday terms. But we can understand it, we can predict it, we can use it, we can build with it. That's physics, not comfort, not common sense. Truth.